This is one of the lengthier lessons that we're going to be covering. So this is going to most likely take us into December. And by the way, this used to be included in the exam in the past, and lesson 15 used to be included. But then I figured, what's the point of rushing things? So I slowed down a lot for more like student understanding and making sure everybody's yeah. Right now, you guys are working with a very nice like timeline. Before, things used to be a lot more stringent because we had so many events and unplanned things happening at some school. All right, so let's go ahead and start with the FTC. Please make sure that you write down all the important rules. I'll tell you what part of these rules is, the most important of those important rules. So rule number 1 is called the first fundamental theorem of calculus, also known as the first FTC. Okay, now when you start writing this down, the one you definitely need to have is the one in the bubble there. Okay, so I will show you everything else and how it comes about. So the first FTC says, look, if somebody asks you to integrate a derivative, also known as an antiderivative of a derivative, well, technically what that means is you're going to go ahead and integrate it. When you integrate it, you'll end up with the function. But you need to evaluate that function over a couple of what we call limits, and so the answer will be f of b minus f of a. Alright? You guys will notice that this actually is also the same thing we said about definite integrals. Okay, so the fundamental theorem of calculus is actually a definite integral. That's essentially where that was born out of. Okay? Now I've put little messages around, especially in this lesson, to help those of you who are like you struggle with just the the math, the formulas and stuff. So just remember, the fundamental theorem of calculus, what it does is it takes an integral of a derivative. Okay, that's what it does. It undoes something that you were doing in part 1 of calculus. Okay. Now take a look at the one underneath it. Okay, don't look at the right side box. You're gonna get confused. So take a look at the one underneath it. The one underneath it says, okay, all right, so now that you've understood the pattern, what if somebody gives you a second derivative as opposed to a first derivative, and they give you even limits for it? Well, I mean, most people understand this logic. So if you take a second derivative and you integrate it once, where would you go to then? You would go back to the first derivative. So I like to call these modes. So you're now in first derivative mode, and so it would be f derivative of b minus f derivative of a. Okay, now the AP exam does not go to third derivatives, by the way, okay, because there's not a whole lot of application to them. In linear motion there used to be, but they took it out of the AP exam, but it's interesting to know. So do you guys remember position, velocity, and acceleration?
Yeah.
Which one of these was the original function? Position, then velocity was the first derivative, then acceleration was the second derivative. So there's actually a third derivative in science. We call it a jerk. Okay, and a jerk is when somebody like presses the accelerator really fast. You feel that snap in your neck a little bit, and it hurts a lot. That's called a jerk. So that very small amount of time, the derivative of acceleration is called a jerk. That is actually the application of the third derivative. So it used to be something we used to talk about in this course, but then we kind of got rid of it. It's not that relevant anymore. Okay. All right. Now this is actually asked about more on the AP exam than that one is. Okay, and most students, the reason why they struggle with the topic out there is because they don't understand this part. So listen to this conversation very carefully, inshallah. The first thing that we're going to do is we're going to go back to the fundamental theorem of calc, the one that's written at the top there, and we're going to change a few things. Okay, namely, we're going to take this over here, and we're not going to call it b anymore. So take a look at all the things that are going to be impacted because of our choice to not call that b anymore. Instead, what we'll do is we'll leave it open-ended. Okay, and by open-ended, we're not plugging in a number, we're just gonna go ahead and call it an x. Alright, so here's how that's gonna actually look like. We'll write down that we've got an integral. Alright, let me write it down over here. We've got an integral that's from a to x, f derivative. I'm gonna purposefully change the dummy variable because the AP exam likes to change the dummy variable from x's into t's to kind of highlight a fact that they're trying to get at. So we'll write down f derivative t dt. Now, let's go ahead and go through this together. What would you guys say is the integration of f derivative then? F of t, agree? Okay, now what are you gonna plug into this? Look at what I did over there. So it'll become f of x minus f of a. So look, basically bring out this conclusion and bring out this conclusion, alright? If you understand it the first time, it's gonna make your life a lot easier. You're gonna be with this until the, basically the month of May. You're gonna keep seeing this in a lot of the lessons. And so now it reads, the integration of f derivative t from a to x is equal to f of x minus f of a. And the last thing we do to rewrite this is we take this term over here and we move it over to the left side. Now algebraically, when you move a term over to the other side, what's gonna happen to the sign? It's gonna switch signs. So it's gonna read f of x is equal to f of a plus the integration from a to x, f derivative of t dt. Now you guys will notice that in there it says f derivative of x dx, and all I will tell you is it doesn't really matter what you decide as long as they match. So if you decided that you'll call this f derivative theta d theta, no problem. F derivative z dz, no problem. Okay, just make sure that the thing inside of the derivative and the dummy variable are exactly matched. Okay, then you're perfectly fine, because at the end of the day, all you're really doing is you're plugging in numbers into that once you integrate it, okay? So go ahead and write this down. This is known as the rewritten version of the FTC. Now there are two FTCs, so every time you refer to this, give me the number on it, okay? Because the second one does something vastly different than the first one here. Okay, now in this, there's a few things you want to write down. One of them is this thing over here. This is called an initial condition. It wasn't really called that over here, okay? That was just initial minus final sort of thing. Here we call it the initial condition. And this part over here is called the change. This is called the change. And this over here is basically your final. You can call it a result if you want. So many things in science, in math, in life are based upon this. Let me give you guys an example, okay? Does any one of you know how tall you were the day you were born?
6
It would say on your birth certificate, but you know, okay, how tall is a baby when the baby's
I think
born?
Like 12 inches.
Okay, fine.
18.
Yeah, they're like 18,
It's like
19,
18 to like 24.
Yeah, 12 is kind of.
No,
Sure.
sorry, 12 is kind of small.
Yeah,
18.
alright, okay.
19.
So, let's suppose that there's a baby that's born, and on their 0th day, alright, they are 18 inches tall. Now, how much does a baby grow in the first year? Give me in inches, because she started it in inches. About
No.
5 inches?
No, they like triple.
They like double quadruple.
Double? Okay,
No, it's
So-
more than.
Or like
so if you
No,
were to
so-
give me a number, how much would you say?
30.
40.
No, they're like 30. No.
No, listen, are you saying they're gonna be 40 when I measure them at the end of that year, or are you saying they're gonna grow 40 inches?
They're gonna be 40.
When you measure
Okay,
it,
so how much is the change then?
22.
22, okay.
Guys, they're more than 30.
So, what you're saying here is from the time that they are born, look at where I put the 0, from the time they are born, to 1 year later, alright, when we take a look at that change and we integrate that change, you guys are saying 22. So again, it should be logical why the FTC had to be rewritten to work with this, because this is a more practical end, and integration is a very practical skill. So basically what we're saying is if you want to know how tall that baby is finally, you're going to have to take what they initially were, because if you miss out on the initial part, you'll be misled to think that they're only 22 inches tall. They're not, right? So you have to take what they initially were, add how much they picked up over the span of a year, and that will tell you how tall that they actually are. Now here's the really neat thing about, here's the really neat thing about integration. What if somebody says, well, I'm not interested in a year, I'm interested in 1.2 years. Well, the really neat thing is all you gotta do is go up there. This is why it's left open-ended. So at the moment that you're interested in a different time, you just go over here and you change up that time. And then it'll just go ahead and add that change. Because realize the initial condition, once it happens, it doesn't happen again. So this is stuck. It's always gonna be 18. You were born the way that you were born. But then, you know, basically based upon your diet, your genetics, or whatever it is, you grow a certain tall amount of height, and so that is going to be accounted for over here. Now, I gave you an example. Now you give me an example. Can you think of something else in life where we have to like sort of initially tell what it is, and then we measure the change of it, and then it allows us to tell what the final is going to be?
Cancer.
Like growing a plant.
How about we not talk about heights, because
Oh, okay.
you know, a child is kind of like a plant too, right? They
Weight.
grow. Weight.
The number of snow.
Cancer.
I like that one. I like that. Inches of snow. Okay, cool. So how would you work with that?
Measuring. Like first we'd see like if it's like a.
Okay, wait. So what's an initial condition
Before
for
it's
snow?
snow, would be no snow.
Zero. No,
Oh, it could be
Or
the
the
first
first
hour.
hour of
Okay,
snow.
here, let's make it interesting. What if there's snow on the ground right now, okay? What if we're talking about tomorrow, alright?
Okay, then
So
you
that's just
measure
your
how much
snow.
today by the end.
There it is. See, initial condition does not necessarily mean 0, okay? It depends on where you start looking at it. So when you looked at it, which is basically tomorrow, you're like, there was already an inch of snow on the ground. I need to account for that before I can tell you how much more we pick up tomorrow. You get it? So sometimes it'll snow and then it won't ever melt, right? All winter, and then more snow gets put on top of that, right? So that is basically your change right there, okay? So this is one of the most central things in calculus, and that's why it's called the FTC. And then we build a lot of things based upon this idea of an FTC right there. Now, something that's logical is if you could do this over here, make sure you write that down, and it would lead to that over there. Well, think about rewriting that same exact idea. So technically, if you were to integrate the second derivative, you would need the initial condition on the first derivative so that you could make conclusions about the first derivative, okay? So you'll notice I just put in a little, one more mark on each one of them. And so then it's like you can extend that theorem. It's like kind of like a corollary. You can say more about the theorem based upon what we just said right there. Okay, yes, please?
So if something is decreasing, your final mass is going to be negative, right?
That's a brilliant idea. Well, can you think of something that initially is something and then it starts to diminish, not increase as it goes along? What's that?
Old people.
What?
Old people.
Like them as a person?
Yeah,
Their
they
height,
get,
I
get
think
taller
she's
and you
talking
start
about the
to
height of old people.
They just get a
Alright, let's
bunch
not pick on the old people.
It's like
Yeah.
I'm living.
Alright,
That's crazy. I was gonna say.
okay, how about a bank balance, okay? So you could look at somebody's bank balance, right? And let's suppose that Brother Asim had $70 to start the day. And then a bunch of girls from the basketball team came up to him and said, hey, you need to buy a shirt from us. And he's like, my kids need to eat. My kids really need to eat. But you know, who says no to these people?
You're not doing any
you
kids,
know?
relax.
And
Just
so, you know, I mean, that's a negative change. That's a negative change right there, right, kids? So that you're gonna go from like a 70, subtract 4 shirts, that's $80 later. So now we're at a negative 10, right? All right, okay, very good. sensitivity. When you go to some of the teachers, not me, when you go to some of the teachers, please realize we make nothing. We literally make no money. Okay, I think we actually lose more coming here than we actually gain. You go and sell them some of the things you guys sell them. You have money, we don't have money, right? So to be like,
Now you guys do.
to be like, can you buy these 20 chocolate bars? We want those 20 chocolate bars. I'll tell you that. We really want that. But we're like, man, I don't think I can afford it. That's the monthly budget right there. So-
Cost money, we were trying to sell it to you guys, I don't know the money ourselves.
Yeah, but they have kids to feed.
Can you put us in debt?
My brother asked
The
us.
teachers, okay, I'll tell you,
To your pockets.
I'll tell you a secret. I'll tell you a secret. The guy teachers don't have money. Okay, don't go to the guy teachers. Be very
Shit.
sensitive when you go to the guy teachers. When you go to the girl teachers, especially if their husband is like a doctor or a lawyer or something, go crazy. Go sell them anything, and they'll be like, all right, that's good. Yeah. Okay, let's keep moving, inshallah.
That's already.
Now let's talk about the second fundamental theorem. All right. The second fundamental theorem is the one that really gets a lot of students confused about, how did this suddenly change? So go ahead and write down number 2, the second FTC. Now, I gave you a little phrase. Do you remember on the previous slide, I said the first FTC is doing what? It's an integral of a derivative. So this will really help if you write down what the second FTC tries to achieve. What the second FTC is actually trying to do is it's actually trying to take a derivative of an integral, more or less. Okay, so that's essentially what's going on. Now the way that it's written is perhaps where people get really, really confused. So because we know that it's a derivative of an integral, we know that the derivative symbol looks like this over here. So d dx, that is the derivative symbol. Now whatever you put in after that, you're implying that you're trying to take its derivative, right? So if you want to take its derivative, the thing you're taking a derivative of is actually an integral. So you write down the integral. Now the limits you want to put on this are really tricky. The bottom limit is going to be some constant, okay? I will make a little note of that for you, and we'll do many examples about this. That right there is a constant. So it's just a number. It could be 1, it could be 2, it doesn't really matter. Eventually, it's irrelevant. But the one at the top, it says u. U is not a constant, it is an expression. Okay, so it's going to be some sort of expression that's going to be given to you. And by expression, it might say x squared, it might say 2x, it might say sine x. It's different things. Sometimes they try to put some really intimidating stuff into that expression right there. And so then, on the inside of this, you want to go ahead and write down f of t dt. Now you may be looking at that going like, Brother Asim, don't you mean something like this? And no, you actually just put down f of t dt. So it's not, you don't put an f derivative in it. And finally, the answer to this is something that none of you could really guess just by looking at it, but it goes like this. You go ahead and you take this function over here, and you plug into that function the expression that is at the top of the integral. Very confusing stuff. So you take this function, just like you did in pre-calc, and you plug this expression into that function. So it's like the f of g of x sort of deal. Okay, so you have to plug that in. So you notice how I never said anything about taking any derivatives, I never said anything about integrating. It's just a interesting process where you take this and plug it in right there. But there is a derivative involved. And I would say even the best students forget this part. The derivative is going to be at the end, and it's going to be times u derivative. What does that look a whole lot like? It's actually the chain rule. Okay, it's a chain rule doing what the chain rule does, but we don't really, it's not so apparent, so we're not going to be like, oh, here's how the chain rule approaches it. We just remember that as the formula. Yes?
So why are you saying like you're taking derivative of the integral if we're not actually taking it?
That's the whole point. We don't want to sit there and actually integrate something, and most of the time it's because literally we don't have the skills to integrate it. Like we just haven't learned those techniques. You'll learn that derivatives, you can take derivatives of pretty much everything. Integration, is a whole chapter just to integrate a certain type of problem. So you guys in AB will only learn 3-4 techniques and you're done. You come back in BC, you learn 3-4 more techniques and then you're done. But you go to Calc 3, there's more techniques. Calc 4 has more techniques, you know? So there's a lot of techniques to integrate. So a lot of times what happens on that is you end up with a function that you cannot integrate. So you are forced to take its derivative and do stuff with it, all right? Now, let's change that up a little bit, okay? You gotta get that thing on the other side as well in your notebook. Let's suppose, the AP exam loves to do this, so let's suppose the expression is simply an x, alright? Now, obviously what you would plug into that right there would be an x, so it would read f of x. But where did the rest of it go then?
So the derivative of 1x.
Alright, the derivative of x is
1.
1, so that's why it doesn't show, okay? And I think because it doesn't show, oftentimes people forget the fact that you're supposed to take a derivative of the expression that was at the top there. It just so happens in this scenario, when u is equal to x, the derivative of x being 1, it just looks like the way it does, okay? We will come back to this and spend a lot of time with the second FTC. Both of these are maybe like, I would say, like a quarter of the exam is based upon these two here. Okay, so that's how important it is. Yes, that's why I took like 20 minutes on it, to explain where we got these things from. Okay, now, you don't need the pictures, but I would recommend you put down this format. And as you're writing it down, I think that it's not that difficult to wrap your mind around this as it is about the first and the second FTCs. Basically it says, look, if you wanted, you could take some areas. Do you have a question?
I was just trying to see the second, do we have to know the second rewritten version of that?
Yes, you do. I can write it for you, no problem. Okay. So, the rewritten version of it is d dx from a to x, f of t dt is equal to f of x, like that over there. That's what it said. My bad. Okay. So basically this, again, every rule I try to just make like an unofficial phrase for you to remember what it's trying to say. Otherwise you kind of get lost in the notations and totally lose sight of what was trying to be said in the first place. It just says, look, if you want a big area, you can pick up small areas and add them all up, okay? So something basic you learn even maybe in elementary school, that you can take areas, add them up, and accumulate more area. So in this scenario, here's what I did. I've got a little problem right here. It says that there's a function, and that's the graph of the function right there, the little red curve right there. And I'm interested in picking up area from 0 all the way to 1.25. So you guys will notice that it's shaded from 0 all the way to 1.25. So the rule basically says that let's suppose separately, for a different reason, you're now interested in the area from 1.25 to 1.75. Again, I think to everybody here it's logical. They would have said the same thing. What I'm trying to get you to do is understand that the notation is trying to say just that fact, okay? So all it says is if you took this area here and this area here, notice how the middleman is 1.25, then essentially what you've done is you've collected a whole area from 0 all the way to 1.75. Now, what's the number that's not showing in the final integral? 1.25. So sometimes you need to figure out where you're going to cut the curve so that you can go ahead and pick up all the areas, and you'll see examples of that in a little bit. But what I've done for you is I've made a bit of a formula, an unofficial formula. AP exam usually gives 1 or 2 questions to see your understanding of this. So I wrote down the same thing, but I wrote it abstractly. So I didn't put numbers in it, I put like letters. Okay, I even highlighted the C for you so you understand what we mean by C over there. Questions? Okay, so that's rule number 3, adding areas. Okay, rule number 4. Now what you need from this, what you actually need from this is this part over here, okay? You don't need any of the stuff that's in the box, okay? That is for me to explain to you. So just put that into your notebook. It's called the average value function. And number 3 was adding variables. I'll just leave a little note here. I won't bother to write it down. Are you guys having second thoughts about integration suddenly? Yeah.
I like from the first day we started, I was like,
Oh, you never trusted it to be like
no,
this?
I love it.
That's the right attitude. Don't trust it. Okay. No, inshallah, you guys will figure it out. We haven't done a single example yet. It's just, we have to establish some ground rules before we get into examples. Otherwise, you'll keep asking me questions about, where you're getting this, where you're getting that, so. Okay, rule number 4 is called the average value function. The average value function, in a nutshell, here's basically what it does. It takes the same thing that we've been talking about, so from A to B, it finds an area, alright, just finds an area. Except, when it says average value, what it does is it multiplies the result by 1 over b minus a. What does that remind you of a lot?
Oh,
1 over b minus a, right? So this is very much like the average rate of change. So this is something that confuses a lot of students is when am I supposed to use the average rate of change formula and when am I supposed to use the average value formula, because they don't generally tell you it's a rate or a value, they just say find the average. So you have to sit there going like, which formula do you want me to use? So can you just write underneath it that you don't want to confuse this, so not to be confused with average rate of change. And just take a moment, write down the average rate of change formula. So f of b minus f of a over b minus a. When your understanding gets a lot better, you'll actually realize they're the same formula. They're not two different formulas. But once again, just like the chain rule, it's hard to make that connection. On a different day, when I actually start teaching these questions, I will come back and I'll explain to you what's happening in that diagram, okay? So the formula is gonna make a whole lot more sense when I'm done with that conversation. Okay, alright, let's write down rules number 5 and 6. These are really quick, okay? Number 5 is known as the reversal rule, alright? Number 5 is known as the reversal of limits rule. So it's basically saying that let's suppose that from one point called B to another point called A, somebody asks you to integrate. You can change the limits. This is where you want to highlight that in your notes. You can change the limits from A to B. And the only thing you need to do is go ahead and compensate by putting a negative in front of the integral. So let me circle the important parts for you. So here's B, here's A. Notice how I reversed the limits, the reversal. So you stick a negative right over there, and then we're good to go. So let's go back to that that baby example. All right. In that baby example, let's suppose somebody said from year 1 to year 0. From year 1 to year 0. Again, so from now to a year ago, how much is the change now technically? Anyone? If it was 22, if they grew 22 inches in the first year, if you go back the other way, it would be what then? It would technically be negative 22 because you decided to look at it in the opposite direction, okay? So, and then we do that sometimes in conversations. We say, they were less than this before, right? So they're much taller now. They used to be less than this. So when you say something like that, the reference point that you're using is actually now, okay? And then you're saying from up until what they originally were. So that is technically a negative 22. But what I'm trying to explain to you is you're still talking about the same thing. If you decide to switch up these limits, you then change the sign from a negative 22 to a positive 22. So it's a quick rule called the reversal of limits rule. All right, rule number 6 is asked every now and then, and this is called the zero area rule. Whenever somebody asks you to find the area from a limit all the way to the same limit, they're just pulling your leg. There is no area that you can actually find. Okay, you just say 0, alright? It's like saying, how much did the baby grow from their first hour in this world to exactly their first hour in this world? Well, they didn't grow anything. You just asked me the same exact time span, right? So nothing happened, alright? So that's a 0. Now, take a look at these. Every year I get different sorts of students. Some of them have forgotten certain things. You're gonna need these a lot on a daily basis. So if any one of these 5 formulas, I know that for ACT you need to know them anyway, but if any one of these 5 formulas is unfamiliar to you, you wanna go ahead and just jot that down. I'll keep asking you about it. Just that trapezoid over there, the way that I taught you trapezoids in geometry was you have a base on the top, and you have a base on the bottom, and then the height is the thing that extends from one base to another. In calculus, we almost never deal with trapezoids like this. We take the trapezoid and we switch it up a little bit, and it looks more like this over here. Just kind of be ready for it. So it's sort of sitting on one of these sides over here. So technically what happens is when we say height, we're actually referring to this dimension now. And when we say base, we're actually referring to this dimension and then the other dimension like this. So base 2. And also what makes it a little bit more challenging is we at some point stop calling it a height because it doesn't even look like a height. We call it a width. Okay, so just sort of be ready for that. When it came to rectangles, do you guys remember in a rectangle what we used to call this dimension over here? Okay. What did you guys used to call this one? We used to call this width. And what do we call this? We used to call this length. I know it's confusing, and believe it or not, because I have to teach all these courses, I have to keep making sure that I don't teach the geometry kids something wrong, or they start a fire. So you got width and length. Now again, what happens in calc is we take this thing, and and you saw the other day when I made those rectangles. What we generally do with these rectangles is we don't actually put it the way you learned it in geometry. We transform it so it looks like this over here. Okay. So it's actually sitting on top of its width, which I think makes a little bit more sense. Okay, so this becomes its width, but here's the kicker. That technically is supposed to be called the length, but we don't really call that the length often. We call it the height. Thank you very much. Okay, so we call this the height. All right, so you just want to make a few notes of that. You're going to get a lot of semicircles, a lot of quarter circles. So there'll be many graphs that you deal with, and you'll be like, man, how in the world do you find an area of something like this? And it's just a circle, okay? It's just a half of a circle. So I put a little formula there for you for a semicircle. They love quarter circles too, so stuff like that. A quarter, it would just be 1/4. Okay, so stuff like that, okay? All right then. You guys have a quiz tomorrow, right?
Wait, what lesson is it on?
Oh, we changed it to Tuesday.
What?
Tuesday's the MLG day.
What? I wanted it.
Oh, you were not here yesterday. Your friends spoke for you, and
Well,
they said
you
Jenna
guys
would
can wait
have
till
wanted
after
to-
Thanksgiving.
No, I said no.